So what we are interested in doing is generating coherent states. Okay, coherent states are typically light produced in a laser. What we produce by these lamps like this is totally incoherent state. So we are not interested in this light. Neither are we interested in sodium vapor lamp and things like that. So our interest is in laser and what we can do with that. Laser means coherent radiation or highly coherent radiation. See, there is nothing like perfectly coherent radiation. Perfectly coherent radiation is a strictly mathematical plane wave. Such a plane wave has a single frequency theoretically, and it extends from minus infinity to plus infinity both in terms of space and time. Such a thing means infinite energy, therefore we treat it only as a mathematical concept. Anything else which you generate in the lab will not be a monochromatic wave. It will be polychromatic. Even if you use an LED, it will have a spectrum. A laser has a more narrow spectrum, that is it. Okay, this source has enormously large wavelength range. Okay, so one aim, if you have followed the literature, one of the aims which is generally observed in the scientific world is to try to generate coherent radiation at different wavelengths. See, you have, for instance, you have a helium neon laser. You are all familiar with helium neon laser. That produces radiation at one specific wavelength. Of course, it has a line width, and that is 633 nanometer. Okay, if you take ruby laser, 694 or something. So different lasers which you actually buy in the market, they will all have a almost highly monochromatic single wavelength output. Okay. What can we do to extend this to get coherent radiation at other wavelengths is an issue. So people have tried all sorts of materials and they have made lasers at different wavelengths. That is, of course, what is existing. You also have semiconductor lasers, and semiconductor lasers to some extent can be operated at over a certain wavelength range. One of the ways of generating coherent light at different wavelengths is to use nonlinear property of the material. Okay, so when you say nonlinear property, what it means is, think of P, D equal to epsilon naught E plus P. That P part of it is in our undergraduate books, it is written as epsilon naught chi E. That chi is a linear susceptibility. But if you use more intensity, P cannot be written just as epsilon naught chi E. It will have to be written as plus some alpha E square plus alpha E cube. E square does not mean multiplication. It means tensor product. EE. Third order would be EEE. E has 3 components. So if you say EEE, total number of options will be 3 into 3 into 3. 9 3 is 27 different combinations. That is the meaning of tensor product. Okay. So materials show optical nonlinearity. One thing which we should note is, see, crystals have crystal symmetry. So there is something called inversion symmetry in the crystal. Okay. Crystals which have inversion symmetry will not show second order nonlinearity, that is EE type of nonlinearity. We will call it chi 2. Chi without any suffix is linear susceptibility. Second order susceptibility is chi 2. Third order is chi 3. We will use that notation. Okay. So when I say second order nonlinearity, it is EE. Okay. So in crystals which have inversion symmetry, this chi 2 can be shown to be 0. In fact, such a thing, such a conclusion happens for piezoelectric effect and all that. So you can look it up. all materials show third order nonlinearity. Okay. When you say inversion symmetry, it also implies includes amorphous materials, because amorphous materials will also have inversion symmetry. So fiber which is made of glass is an amorphous material. So therefore, fiber will not show chi2. Okay. So what is the first nonlinearity in the case of optical fiber? It is chi3. Okay. So let's remember that. So if I am using a crystal, I could be exploiting chi2. Now another difference you should note is this, the most prominent contribution is the linear contribution, epsilon naught chi e. Okay. Epsilon 2 EE is a much smaller term in the expansion. Okay. That will become prominent only at high intensities when E is large. Chi2 is a very small quantity compared to chi. Chi3 is much smaller than chi2. So it's like a series expansion in which successive terms are much smaller. Okay. So therefore, normally if you look at books or papers, you will not extend much beyond third order nonlinearity. Okay. So we will see how chi2 and chi3 help us to generate photon pairs which have correlation. Okay. Of course, I also mentioned that what happens in a laser, or a laser produces what is called as coherent state. Okay. Coherent state is very different from this, because you would have done experiments with laser. Even if you shine laser on a surface, see, I see this surface without any granularity. Even if I have a smooth surface like that, this light which is falling on that shows that it is smooth. But if I shine a laser light on you can try this in the lab. On a smooth surface, you shine laser light, it will appear grainy. That is one consequence of coherence, because coherent radiation easily forms fringes, or forms fringes which are easily visible because of its coherence property. In fact, quality of interference fringes is a measure of how coherent a light is. There is something called visibility of fringes which you can calculate. The visibility is high, coherence property is better. Okay? You can see in such definitions in any book on optics. Okay. If I want coherent light, I just use a laser. But if I want squeezed light, or if I want entangled photons for my experiment, then I have to use either chi2 or chi3. The fibers microstructured fiber which I described in the morning, that is the type of fiber which is suited for exploiting chi2 and chi3. So our devices with which we will generate entangled photons or squeezed photons, okay, there we will use the microstructured fiber. So what are the microstructured fiber? The ones with solid core or the ones with hollow core? Both can be used. In the case of hollow core, we have to fill it with certain gas which will behave as a nonlinear material. Okay, so that is what I have stated here. We want generation of entangled photon pair for many applications, and we can generate correlated photon pair or entangled photons, light made up of entangled. See, entangled photons consist of photon pairs. There is a phase correlation between specific pairs. So like that, there are multiple pairs which are there in the beam. Okay, that is the speciality of light beam with entangled photons. Okay. What is so great about entangled photons? Entangled photons are also we can show that it is in the squeezed state. Okay. I will explain what is the implication of squeezed state a little later. Okay. So first let us see by what process you can generate entangled photons. Okay. So as I have stated there, parametric down conversion is one mechanism to produce entangled photons. Other than that, so the first one, parametric down conversion, is a typical process in a Chi2 material. Okay, a material in which Chi2 is prominent, like crystals. Okay, but if I am taking a fiber, Chi2 is 0, so there this process will not work. The so-called parametric down conversion will not work. Okay, in that, so in fibers, there is another mechanism called four-wave mixing. Okay, I will explain what is the meaning of parametric down conversion and four-wave mixing in a moment. Okay, so in fibers, it is a slightly different process, but it generates photon pairs, correlated photon pair or entangled photon pair. Okay. See, Chi2 material at sufficient, if you pass a beam of light with sufficient intensity through a crystal like KDP or KTP, okay, nonlinear crystal, if you pass a beam of light, output is two beams. The two beams may have same frequency or different frequencies. So output would be either omega plus omega or omega 1 plus omega 2. Okay. Input light has to be something, in the first case it has to be something like 2 omega, because we want to conserve energy. Do you understand? Here's a crystal, light, I pass light through this is a nonlinear crystal. This light consists of photons. I want energy of the photon, incoming photons, to be equal to this number 2 omega h cross. H cross omega is the energy of the photon, right? If a photon frequency is omega, what is the energy content of a photon? H cross omega. But what I want is 2 times h cross omega. So photons with energy 2 times h cross omega enter the crystal. What comes out of it? H cross omega plus h cross omega. So the input energy is balanced by the output energy. Okay, and this happens with almost zero loss, almost zero energy loss. Okay. Note that this requires that atom or a material. This interaction happens only through the material. Okay, but it's a very special process. The special process is whatever the photon which comes out here, the photon pair, you can show that they have a phase correlation. Yesterday, Usha madam was describing the issue of entanglement. She said, I send one photon this way, another photon this way, I make a measurement on only one side, I get information on the other. That is the speciality of entangled photon. So it is very special light. Okay. So here is this mechanism called frequency down conversion. You have a high energy photon entering, and that photon energy is divided into two parts. If it is divided into two equal photons of equal energy or equal frequency, it is called degenerate mechanism. But it need not be equal. Frequency of one photon can be different from the frequency of the other photon, but their energy sum should balance the input. Energy conservation is. Another thing is, in all these processes, phase matching has also got to be satisfied. Phase matching is like this. In the crystal, the beam propagates. Okay. At each point in the crystal, this generation of photons with frequency omega 1 and omega 2 happens. Okay. But if the frequencies are different, the phase velocities in the crystal will also be different, right? Light of different, what happens in a material medium if you push light of multiple wavelengths? They will travel with different speed because the the refractive index at different frequencies is different. So because of this phase velocity mismatch, the process will come to a stop because both the waves have to travel together. Okay, this is something which is called phase matching. If you can read up details about this in the book. So any nonlinear process, whether Chi2 type or Chi3 type, has to satisfy two things: energy conservation and phase matching. Okay, we will not bother about details of phase matching and all that. It's a elaborate thing which you can find out from books. Energy conservation is more simple to understand. Okay, so I have both varieties. If the frequencies are different, we call it degenerate. Sorry, non-degenerate. If the frequencies are equal, it is called degenerate. Degenerate means same photon state. Okay. If the frequencies are different, it is called non-degenerate. Okay. So both degenerate and non-degenerate entangled photons can be generated by Chi2 process. When will it be degenerate and when will it be non-degenerate? Depends on the phase matching. Okay. So the phase matching will decide what will be the output. Now, how do you manage this phase matching? Phase matching can be managed by rotating the crystal. You have the incoming beam, you have a crystal, you can reorient it. So by carefully reorienting, you can select which process you want. Okay. Alternatively, you can also manage the temperature variation and achieve phase matching. There are techniques to do that. Okay. So I can have a source which gives me non-degenerate entangled photon pair output or degenerate photon output. Okay. So Chi2 is just this division of incident photon into two photons. Okay. What about Chi3? In the case of Chi3, the process is, see, in Chi2 process, we are dealing with three waves. So we call it three-wave interaction, three-wave mixing. Which are the three waves? Input and two output. So there are totally three. Chi3 process is called a four-wave mixing. Okay. So what is the meaning of four-wave? I might have one intense laser beam coming into the crystal. Okay. What comes out is 3. So 3 plus 1, 4. Alternatively, I can have two waves incident, generate two more here. Okay. So at the output, I have either two photons coming out or three. Out of them, so whatever photons I output here, if I get three, look at the process which gives me three photons. For one incident photon, three photons coming out. Sometimes this is called as third harmonic generation. Okay, because the frequency energy gets divided, may get divided equally into three photons. Okay. Alternatively, I can have that is degenerate process. Even those three photons are correlated. So it's a three photon correlation there. Okay. Alternatively, if I have two input waves, get two output waves, those photons will be correlated. Okay. So that it would be two photon correlation or entangled photon pair. So entanglement can happen between two photons or three photons. As I said, most interest is in Chi2 or Chi3. So we'll bother about only these options. Okay. So I hope you have followed why we need a nonlinear medium. Why do we need a nonlinear medium? So that I can generate entangled photon pair. Okay. Why do I need an entangled photon pair? Now let me try to explain. If I have coherent state, photons in coherent state, then I can show that the uncertainty in, let us say, the amplitude. So when I say photon, I can talk about the electric field of the photon. Okay. Electric field means not only magnitude but also phase. So I have two mathematical quantities which may need to be measured, and there can be fluctuations or errors associated with this. So amplitude error, phase error. You look at the product of that. Okay. So you can show from Heisenberg principle, starting from Heisenberg principle, that the error in amplitude times error in phase, okay, that product must be something. Heisenberg's uncertainty principle says it should be equal to greater than h cross or h cross by 2. Some people write h cross by 4, doesn't matter, h cross. Okay. And the same principle applies to these photons, entangled photons also, or coherent photons also. But coherent state is a very special state in which the error is minimum, which means it tallies with delta E delta T equal to h cross, not equal to greater than, equal to h cross. So we say that this is the minimum error state. Okay, minimum uncertainty state. Uncertainty into of amplitude time uncertainty in phase equal to h cross by 2. Of course, this is formulated even in slightly modified form. Some people define two parameters called x1 and x2. x1, both are defined in terms of the creation and annihilation operator, which you are familiar with quantum mechanics of harmonic oscillator. Okay. So you can define combinations of creation and annihilation operator suitably. You get two parameters, because creation and annihilation operators are two. Using them you can define two parameters. Instead of using those, you can use x1, x2. So if you look at x1 is defined as 1 by 2 half A plus A dagger, where A is annihilation operator, A dagger is creation operator. The other parameter is defined by 1 by 2i A minus A dagger. Okay, this is the definition. If you use this, you can show mathematically that the uncertainty in x and the uncertainty in x1 and uncertainty in x2 product is 1 by 4. Some authors may get 1 by 8, doesn't matter, it's some number. Okay. So for coherent state, this is the minimum product of uncertainty which is satisfied. So it's a very special state. Okay. Which means for a coherent, with coherent photons, if you do a measurement, you will get equal errors in both amplitude and phase. Okay, half. All right. If I now look at entangled photons, you can show that delta x1 can be less than half, or delta x2 can be less than half. What did I say earlier? Delta x1 times delta x2 is equal to 1 by 4, which you can treat as half into half. Okay. Entangled photons, or light consisting of entangled photons, have the property that delta x1 is less than half, or delta x2 is less than half. If delta x1 is less than half, delta x2 will be larger. This is the consequence of squeezing. What is the meaning of squeezing? So delta x1 becomes smaller than half. How much smaller? It depends on the conditions under which you create that. It could be instead of 0.5, it could be 0.3, 0.1, whatever. So the error is reducing. Do you understand that? Error in measurement of x1 is delta x1. Same as in Heisenberg principle. Your Heisenberg principle is delta x delta p equal to greater than h cross by 2. What is delta x? Error in the position measurement. Delta p, momentum measurement. What am I saying now? Delta x1, delta x2. x1 actually corresponds to, in a way, to position. Okay, position for the harmonic oscillator, for which the solutions are the coherent states. See, basically what we are doing is, if you want to talk about quantum nature of light, you have to imagine radiation in a cavity, as Professor Mallesh was describing earlier. Radiation within the cavity is modeled as a collection of harmonic oscillators. Okay, and the quantum mechanical solutions of a harmonic oscillator can be used for describing the radiation trapped inside a closed cavity. Means something like this, walls on all the sides. So the radiation is trapped here. Even classically, if you look at that radiation, you can split it into three parts: radiation going up and down, radiation going front and back, radiation going from left to right. If you have waves going both ways, what is formed in between? Standing waves. Okay, so this is another way of understanding. So you have standing wave formation from left to right, standing wave formation from up and down, standing wave formation front and left. Okay, so this is what happens when we model radiation inside a cavity as a collection of harmonic oscillators. That is why I am talking about creation operator, annihilation operator and all that. Okay, so in entangled state, delta x1 can be less than half. How less? It depends. So you can reduce it. You can reduce it to as small a value as you want. Of course, what about the error in the other one? Delta x2 will keep going up. It may even exceed, the product may then exceed half. Doesn't matter. What have you achieved? Error in one measurement is reduced, so you are measuring it more accurately. So the use of entangled photon is to make very accurate measurement. I told you one of the objectives of quantum phenomenon is to make very sensitive measurement. Even in LIGO, this is what was done. Okay, to make a very fine kind of measurement, you have to use light which basically is entangled photons. Okay, so that is one of the secrets of LIGO. So how can we achieve this? You can naturally achieve it in a solid core PCF, because solid core means the central portion is glass. Glass is nonlinear in behavior. It will generate entangled photon pair. If you use hollow core fiber, what you need to do is you have to fill it with a gas, appropriate gas with a proper nonlinearity. Okay, so you can use hollow core fiber also to make a beam of entangled photons. So this is one thing which I thought I should convey to you. You can read up the details in the review paper which I have shared with the audience. Okay. Huh? See, one thing is the method by which you produce it. Okay. Secondly, when you do a measurement, okay, if you can progressively keep on reducing the error, that means you are using, okay, but the method itself guarantees, people have checked it out, method guarantees that it is entangled photon. Probably the issue would be how much is that delta x1 bit. Okay, that I think if you refer to some article, you can figure out how to get that. It cannot be made 0. No, 0 means right side is 0. That
one parameter, maybe delta x, can it be made practically 0?
As far as I know, you can reduce it. Then what happens is that the other parameter, if momentum is totally uncertain.
I don't care for that. So delta X, my interest is only delta X. So like the delta P goes into P. So can this be made zero?
Maybe Professor Mallesh can provide an answer. Squeezing, the circle becomes a ellipse. Can you collapse the ellipse into a line?
Mathematics allows it.
Physically, it may not be possible.
The problem is there is always some.
See,
the emission of any light or anything itself is a damping mechanism.
Yeah.
So if you want light, you have to also ask for the damping. So if you don't want delta, it means that you don't want damping at all. So you don't get very production process itself is one of the ingredients.
My question is, yeah, exactly. So there is some limiting factor acting on it.
What is the fundamental limiting factor? I am not able to answer right now. But obviously, you use any material. Okay. So there is always a excited state lifetime. So such basic things will limit how far you can reduce. But maybe we have to look at literature and find out. So here this just shows that basically is two photon source made out of fiber and thin film devices can be constructed so that, see, the part B shows the red line arrow pointing downwards is a photon with twice the energy, and the blue ones are the photons which are produced. They have equal energy. So this is a process of degenerate photon pair. The last one is third harmonic generation. Single photon gives rise to 3 photons of equal energy with frequencies 1/3 each. Okay. So both of this, which I have already described to you, I will not. So very briefly, photonic crystal fibers, whether they are solid core or hollow core, both can be used for generating the right type of light which we want in the experiment. Okay. One more issue in quantum systems is to convert the frequency of a light which is already being used. So within the circuit, optical circuit, at some stage I may want to change the frequency. So how do we do that? Again, we use the chi2 nonlinearity. Using chi2 nonlinearity, as we have just now seen, you can the incoming photon can be split into 2 photons of different frequencies. One of the photons, if you want, you can reject it by some mechanism, but this is a tunable process to some extent. Okay, so you can by properly orienting the crystal, you can tune what is the output frequency. So you have some input frequency and you can get the desired output frequency by manipulating with the crystal. Okay, so that is basically the mechanism for doing frequency conversion. Okay, so frequency conversion efficiency of something like 30% have been achieved in some devices. So typically, even in chi2 process, typically the conversion efficiencies are of roughly of this order, 30% or 35%. Okay. I will leave this out. What this slide contains is, once I have done something with photons at one node, I want to transfer it to some other node. Okay, so that is called the long distance communication. I want to do that preserving the property of light which is generated. I might be using a squeezed light here, or I might be using coherent light. I don't want that to change. see, in a normal optical fiber, when the beam propagates, there are different things which happen because glass is inhomogeneous. It can scatter light. Okay, so we want to avoid such things. So in order, and also I want to, if it is a pulse, I don't want it to spread too much. So for both these objectives, it is better to use a microstructured fiber like a PCF, because what is PCF? PCF transfers single mode light. So if I have designed it for a certain wavelength, I can pass that light through the fiber to some reasonable distance without distortion of the pulse, okay, and preserving the phase correlation. So long distance communication is also one would like to manage using a solid core, preferably a hollow core PCF. Why hollow core? Because hollow core, see, if I use a solid core, there are nonlinear effects. So when I pass this light, further nonlinear changes can happen. So I don't want that. So for that, hollow core fibers are employed for transferring light signals over a certain distance. You cannot do it for too long a distance, maybe several hundred meters or 500 meters. So the longest communication link for such purpose has been something like 7 kilometers or so, but this is a very special case. Okay. By the way, all these are laboratory, results. They are not in the field. Nobody has implemented this yet. Okay. So it's evolving quite, significantly and quite rapidly also. So somebody wants to get into this field, this is the right time. I've described to you about squeeze photons. So, by the way, as I said, you can borrow this PPT and you can read it up yourself. Okay. So some details I will skip. This shows, at least you can see that a microstructured fiber, this is the core. This portion is expanded here. Okay. So this core, the structure of the core can also be redesigned. Earlier this was either an open portion or it was solid glass. In this case, only a small middle portion is hollow or filled with glass. So there is a certain structure in the core area itself. Why is it there? Again, it may have to do with managing the dispersion. Okay. So you see the significance of controlling the dispersion. In microstructured fiber, one of the main things is how to design the fiber so that it has a particular dispersion property. Okay. So dispersion engineering is the name given to that. I think this also more or less I have described to you. Here is fiber gas cells. So obviously here I will use hollow core fiber. Okay. Let me describe the thing here. See what you see. This is a scheme for to store some data. Okay, you want a memory element. So what is the scheme? The scheme is you have a hollow core fiber which is filled with a certain material. Okay. You excite it using two lasers. Okay. This is called signal and this is called a control field. What you want to store is this. Okay. So this excitation will happen only in the presence of these two. Okay. So we can use this control field to kick the atom to the excited state, and hopefully it will remain in that state for some time. See, even in excited states there are what are called as metastable states. Metastable states stay in that excited level for a long time. Okay. If I want to pull it back, again I put a pump, the same pump, and de-excite it. Okay. So you can store the information or the information in terms of excitation, which means you are storing that yellow photon corresponding to that yellow line. Okay, and you can also evacuate that. So
delta S and delta C.
See, this is the virtual level. This is basically it's a 2-photon process. 2-photon process can happen through a virtual level. So what is this system? It has a pump laser coming from here. This is, see, you put a quarter wave plate, okay, to alter the state of elliptic polarization in general. So the quarter wave plate will help you to choose a particular polarization. So you have a pump coming from one side, you got a signal coming from the other side, both of them enter into this cavity, this thing happens, and then the information is stored between the two levels. Okay. Then if I want to measure the output later on from this cell, it of course can go this way as well as this way. Here I have a polarizing beam splitter. PBS is a polarizing beam splitter. So it will reflect a particular polarization. So that is why I need to prepare these things in a particular polarization. So I do this detector. This is a bulk thing, big and so on. How do I implement this to miniaturize this? That is shown over here. Okay, so you can take a look at that. It has the same, by the way, in one of the experiments, what is filled in here is rubidium vapor. Many experiments are done using rubidium vapor. So the same process can be implemented using, see, these beam splitters can also be made using fibers. There is something called fiber Bragg grating in a fiber. It acts like a filter. Okay, so it will send one beam through and send back the other beam. So for a lens, I can use a graded index fiber, small segment of graded index fiber. So this entire thing can be implemented, miniaturized using fibers and thin film devices. So that is the ultimate objective also. Since the system consists of many parts and light is traveling from one part to the other, what happens is, if I am producing light from a source and I want to pick it from a light from a fiber, I need to couple the light coming from here into this. Or if I have some other device, there also I will have to transfer light from one point to another point. So this process of transferring light involves some kind of joining of this. So we call it coupling. Okay. So, or connectorizing. For instance, I have two fibers. Suppose a fiber breaks. Then what I do is I bring them together and join it by fusing. So that is called a connectorization. Or I may have a single mode fiber and a multi-mode fiber. So I hope you understand the significance of it is like connecting wires in any electronic circuit. These connectors have problems of their own. because of the mismatch at the joint. Okay, so mismatch can lead to attenuation, it can lead to phase distortion, and so on. So there are issues like that which have to be sorted out. So I have listed some of them, and you can take a look at it. Okay, so for instance, I may be interested in connecting a hollow core fiber. Hollow core fiber has an internal geometry which is different. I may want to connect it to a single mode fiber. Single mode fiber core is very less. Okay, so that matching has to be done. So some of these I will indicate here. Here is the stuff. This single mode fiber, the core is only small thing here, white spot. This is hollow core fiber. The core is bigger size. So when I connect this end to this end, this output is seeing only a small portion. This is an issue in connectorizing. Okay, how can I solve this? Single mode fiber, it has a certain signal which is coming in. What I do is I use this section. GIF is graded index fiber. So this will act like a lens which will expand the beam. A thin beam entering the graded index fiber piece will come out as a larger beam. Okay, this is what is called as mode matching. This mode size, transverse size is less. I use this lens to expand it. Expanded portion matches with this hollow core fiber. That is how I establish a connectorizing. Okay, so like that there are other schemes which are mentioned here. Okay, for instance, here is something which is interesting: thermally expanded core, in which if I slightly make the one part of the fiber warm, its refractive index will change a bit, and therefore you can afford to get this beam size expanded to this, and then it enters the other thing. So when it is entering the other fiber, its mode size must be the same, otherwise there will be losses. Okay, so this is another interesting outstanding problem in photonic systems. So what is the outlook? Microstructured optical fibers have many applications. The reason microstructured optical fibers are nonlinear materials. Secondly, they carry a single mode. Okay, both hollow core fiber and solid PCF refers to solid core fiber. Okay, are being explored for fabricating sources and also detectors for non-classical light. What is non-classical light? Coherent light, which is generated by a laser. What else? Squeezed light. How do you generate squeezed light? I just now told you. Pass the laser through a crystal, or a nonlinear medium. What light comes out of that is a squeezed light. Please at least remember this, so that later when you do internet search, you know what you are reading. Okay. Challenges include low loss interconnects. We have to bother about the interconnects. We have to reduce the energy loss. Always the motivation is to use minimum energy to do something, to transfer data from one point to another with minimum energy budget. Okay. And also control the dispersion. Why do I want to control the dispersion? Because I don't want the data to merge into each other. Okay, the pulse spreading has to be controlled, and so on. So all this I have picked up from this reference. This is a review article published in 2024 So it will give you an up-to-date idea of what is happening here. Okay. So that's my first lecture. What is the time?
5 minutes past 3.
Yeah, I had only 1 hour, right? Huh? 45 minutes? 40 minutes. Okay, in that case, can I get the other? I have prepared one more presentation on terahertz sources. See, what have we have been discussing source of light which is appropriate for certain quantum applications. Okay, so in the same spirit, I would like to present to you certain methods to prepare coherent radiation at terahertz frequency. What is terahertz? 10 to the power of 12. Okay, gigahertz is 10 to the power of 9. 10 to the power of 12 is terahertz. This lies in far infrared. Okay. So I'll quickly give you some idea, and you can see the PPT presentation for details. So there is great interest in producing coherent light at different wavelengths, as I mentioned in the morning. The people have tried to make coherent radiation at X-ray wavelengths. See, X-ray tube which you use in your laboratory for X-ray diffraction and so on, it's not coherent radiation. Okay. You know how X-ray is produced. You have a high energy electron beam hitting a target and all that, but that is a totally incoherent process. So how do you get coherent X-rays? There are techniques to do that. Long time ago, I have worked on one experiment to make coherent X-rays at soft X-ray wavelengths. So there are different processes for generating coherent X-rays. Are they important? Yes, they could be important, because what you can achieve with any coherent radiation, you can achieve with X-ray coherent X-rays also. So it's of great interest. Similarly, see, what I produce at kilohertz or megahertz frequency range is highly coherent. Microwaves can be highly coherent. What is the meaning of that? I can generate a microwave which is almost resembling a sine wave or a cosine wave.
Maser is question.
Yeah, maser was a special technique, but generating microwaves using a klystron or a gyrotron is basically involves making an electron go around in a certain orbit within a cavity, resonant cavity. So the process by which the electron goes around, it is not quantum mechanical, it is classical. It is totally under our control. How fast that those electrons will travel, or what is the current, all that is well within our control. So if you look at the waveform of a microwave, single frequency microwave, on the oscilloscope you will see a nice sine wave. That is an indication that it is coherent. Why is it coherent? Because the process decides whether the radiation is going to be coherent or not. We have no control over this process. You just supply electrical energy, gas heats up, it produces light. So that's it. You cannot control the actual process of light emission, right? So this is incoherent. How do you convert incoherent visible light into into coherent radiation? Laser. Again, I will not go into the details of how that is done. A laser is a special device in which radiation is generated in a cavity, 2 mirrors, and mechanism which operates there is stimulated transition. Okay. So compare that with what you do in a klystron by driving an electron in a certain orbit. Okay, like a synchrotron. What do you do in a synchrotron? You have an electron beam or a proton beam, you take it around by magnets, electric field and all that. You have complete control on that radiation. So, if I want to generate terahertz radiation which is coherent, okay, till now people have not discovered any material with which you can produce laser like radiation in terahertz frequency. What is terahertz? Is something like 300 gigahertz, sorry, this so-called terahertz radiation stretches from about 300-400 gigahertz all the way up till 10 terahertz. All that entire spectrum is called terahertz radiation. Okay. See, there are techniques to produce radiation up to 90 gigahertz or 140 gigahertz. Beyond that, the process is not very clear. Okay. So, how do I produce coherent terahertz radiation? I do it with nonlinear mechanism. Okay, same mechanism which we have been discussing so far. So, nonlinear mixing of laser radiation in nonlinear crystals will help us to produce coherent terahertz radiation. Okay, how we will see shortly. What is the application of terahertz radiation? See, if you produce a radiation, you have to use it for some purpose. Till recently, all spectroscopy was done either in visible range. See, all of you would have learnt about spectroscopy. You would have done visible light spectroscopy, X-ray spectroscopy, IR spectroscopy to study materials. So, spectroscopy at terahertz frequencies was not in vogue till recently. Okay. What does spectroscopy give us? Why do we at all do this spectroscopy? Any idea? It is not to pass MSc examination. It has a wider objective. What is the objective of spectroscopy? Those who do material science would tell me. To study the properties of materials, okay, characteristics of materials, very simple. So, spectroscopy is a very important thing. See, when I was doing MSc, we gave last priority to spectroscopy. It was a very bad policy. And spectroscopy is not just visible spectroscopy. Nowadays, it has gone to all parts of spectrum. Okay, so if you have a chance, learn something about spectroscopy. So, one objective is to do spectroscopy at terahertz frequencies, for which I want coherent radiation at multiple wavelengths, terahertz domain of course. Second objective is, the first one is imaging, not spectroscopy, imaging. Okay. Now, this imaging is something which is very interesting as far as terahertz frequency is concerned. People want to use it in the airport for screening. Okay, what can it detect? It can detect explosives. So, you see the usefulness of terahertz radiation. Terahertz radiation can go through the suitcase, but if there is a material of a particular type, it gets absorbed and you can see a signature. So, airport screening is one place where imaging is. Another that application of imaging is in manufacturing. In manufacturing, you want to see what is the geometry of the object and so on. Okay. So, for that also you can use terahertz radiation, because it can go into a region where visible light cannot go. See, visible light cannot go through this chair, but terahertz radiation can go. You can see what is on the other side. Okay. So, imaging also is an important thing. Then third thing is of course communication. It is expected that, so we will go into 5G, 6G, 7G, 8G and so on. At some stage terahertz radiation will become important. I may tell you that communication and communication systems at 90 gigahertz and 140 gigahertz and so on are practically useful. such systems are used in, for instance, in ships for communication, okay, from deck to lower deck and so on. So these are not useless things. That is what I want to tell you. Okay. So terahertz wireless link is another application where terahertz radiation would be useful. And the same things I have added a few more things. Terahertz water or moisture absorbs terahertz radiation. Okay, so this is also important. You can monitor. You can monitor water content in any sample, including human body. Okay. You can also study. See, terahertz radiation is far from infrared. What is the source for infrared radiation? See, for visible light, what was the source? What was the mechanism? Sorry, not source. What mechanism produces visible photons? Electronic transitions. Okay. What produces IR? Infrared radiation? Molecular vibration. Okay. You also have rotation degrees of freedom. You have combinations, rotation vibration states. All those rotation vibration states lie in the terahertz domain. So if you want to study those degrees of freedom for a molecule, then terahertz radiation is a required thing. I will drop this. I will just mention generation of terahertz radiation. We have already discussed frequency down conversion in materials which have Chi2. So frequency down conversion is a good method for producing terahertz radiation. How? Now what I do is, I have a crystal, I send two photons at frequencies omega 1 and omega 2 such that omega 1 minus omega 2 gives me a frequency which lies in the terahertz region. Okay, so using a Chi2 I can do this also, generate difference frequency. Okay, so one method is to use Chi2 in a material, do a difference frequency generation using two photons, input photons, and that difference frequency could be in the terahertz frequencies. Okay, so this is one way of producing terahertz radiation. I can also use Chi3. Okay, I can also use Chi3 because with Chi3 also I can generate a photon pair in which the frequency difference can be in the terahertz domain. Okay. So I will illustrate this. Why am I going back? This slide shows you three different ways by which you can generate terahertz radiation. So I will describe this and stop here. See, one process is to exploit Chi2. Okay. Using Chi2, what I can do is I can choose a continuous wave at two frequencies, 1 and 2. This is in the near infrared, just beyond optical, high frequency. When I mix two waves, two sound waves going in the same direction, what do I get? I mix two sound waves of slightly different frequency going in the same direction, beats. Okay, what is a beat? A pulsed waveform, high frequency thing, and then another high frequency thing. So it's in the shape of a pulse with high frequency radiation inside. The envelope is lower frequency. The envelope frequency will can tally with the terahertz radiation. Okay. So what we do is we use this to produce. See, this is like one piece of that beat. Okay, the beat signal. If you remember what happens in sound, its envelope goes like that. So pick one of that cycle. That will be a pulse. These two triangular kind of pieces are metal, aluminum, silver, gold, whatever, high conductivity metals. They can do the work of an antenna. What kind of antenna? Thin film antenna. Why do I want thin film antenna? I want to miniaturize. So this antenna will have a acceptance or emission characteristic which resonates with a certain wavelength. So you can build antenna. See, the same antenna cannot pick up radio signal and television signal. Have you seen that? For satellite communication, you have a dish, and the dish is large, but the antenna part of it is, the detector part of it is small. Earlier, when we used to use radio when I was a little boy, there used to be a jali kind of thing which was spread somewhere. Most of you wouldn't have seen that. Even for television, we used to have that metal aluminum thing with several sections, right? So antennas have to be designed for to receive or emit at a particular frequency or wavelength. So this kind of antenna, thin film antenna, is designed like that. This pulse comes in here. It interacts. This is a waveguide section built into the antenna. See, it is always built at the middle. This entire stuff is the antenna, Terahertz antenna. So here there is a gap. This gap is filled with a nonlinear material. This will interact with this nonlinear material. What is the result? Difference frequency, chi 2. So because of the chi 2 nonlinearity here, a radiation at the difference frequency is generated, which is in the terahertz domain. That radiation matches this antenna property, filtering property, and the radiation can be emitted. So this is how one way of exploiting chi 2 to generate terahertz radiation. What is done here? This is slightly different. Okay. In this, what is done is, these are circular fiber loops. Such a loop is treated as a ring resonator, optical resonator in the shape of a ring. Have you heard of optical resonator? Two mirrors which are kept like this with light in between is an optical resonator. That is what is there in the laser. Instead of that, what I have is a fiber is going round. That can also function as a resonator if certain phase conditions are satisfied. This fiber can be made of a nonlinear material. It could be a solid core multi-structured fiber. I am going to exploit chi 3. Okay. We use a pair. So these are coupled resonators. Resonators are frequency selective. Optical resonator, like a Fabry-Perot cavity. You would have studied Fabry-Perot cavity in optics. Okay, same principle applies here. So a continuous wave in the infrared region, infrared wavelengths, goes through this device. The result is generation of multiple frequencies. See, Chi2 or Chi3 process can cascade and produce different frequencies, multiple number of them, not just two. The sidebands are not just two sidebands. Okay, so multiple frequency, but in the NIR spectral range. NIR does not mean one wavelength region. What is visible region? 4000 to 7000. NIR would be some 4 micron to 10 micron. Okay. When you mix all this, when you mix light of multiple frequencies, you generate a pulse. Fourier transform theory. If you want to produce a pulse, you have to mix waves at several frequencies. For the number of frequencies, sharper is the pulse. Please look it up. Okay. So I have large number of these wavelengths. They will generate a pulse just like this. That envelope of the pulse will have a frequency which is in the terahertz. So similar stuff. So these pulses which are generated, these envelope will have a corresponding frequency which is in the terahertz range. Okay. What does it do? It falls on a photodetector, high speed photodetector. What happens in a photodetector? If light is incident on a photodetector, it generates a photocurrent. Excess charge carriers, which will, because of the bias, which will result in a photocurrent. At what frequency? Terahertz frequency. Okay. So in the photodiode, you have a photocurrent oscillating at terahertz frequency, and you can design the photodiode appropriately so that it is radiated out. Okay. So something similar happens here. It depends on photoconduction. Once again, it's current flowing in a intrinsic region of a pin photodiode. Okay. So this is how we produce terahertz radiation. Okay. There are different issues which needs to be. This is also an evolving field. This started something like 22 decades back, and it is still evolving. The challenge is to miniaturize components, find new sources, new detectors. Okay. So I'll stop it at this.
Same reference as
No, the reference is different. Where did the reference go? Sorry.